All right, so we're going to go ahead and do the video notes for the first two sections in Unit 2, Equations and Inequalities. A lot of the stuff in this unit is going to be knocking the rust off, at least here in the beginning, and talking about some topics that you should already be pretty familiar with. There might be some expansion upon a few topics or approaching problems from different angles, but there shouldn't be anything that's a total curveball coming at you here in the next couple of days. So 2.1 is rectangular coordinate systems and graphs. So our rectangular coordinate system, it's nothing more than the Cartesian plane or our XY axes. All right. Remember, X is our horizontal axis, Y is our vertical axis. Our quadrants start in the top right, quadrant 1, and they go counterclockwise, quadrants 1, 2, 3, and 4. All right, hopefully you guys remember your quadrants from pre-calc, especially with your trig functions. But if you don't, here they are again. A couple of formulas that are going to pop up as we go throughout. The first being the distance formula. So the distance between any 2 points, let's call those points A and B, is equal to the square root of the quantity x sub 2 minus x sub 1 all squared plus y sub 2 minus y sub 1 all squared. The distance formula, and the reason I have this graphic over here, like this is something that's kind of hard for some people to remember. But let's suppose that I square both sides of my equation. What I end up with is d squared equals the difference of my x coordinates squared plus the difference of my y coordinates all squared. That should look kind of familiar, or at least maybe starting to look kind of familiar. Isn't this no more than a squared plus b squared equals c squared? Where a and b are simply my horizontal side lengths. So if you look at my graphic over here to the right, here are my horizontal side length. You could call this distance a. My vertical distance, we'd call this b, right? And if I had a squared plus b squared, I end up getting my hypotenuse, or c squared, right? And that hypotenuse is simply the distance between my 2 points. Okay, so if you ever can't remember the distance formula, just remember that it's really nothing more than Pythagorean theorem applied to the distances of horizontal and vertical difference of points. Okay, so it's one easy way to remember it. Like I said, a lot of people, once I show that to them, they actually remember it as the Pythagorean theorem more than they remember the actual formula itself. So using the distance formula, obviously if I have 2 points, let's say 2, 1 and negative 4, 3, I want to label x sub 1, y sub 1, x sub 2, and y sub 2. All right, it doesn't matter which one I label as point 1 and point 2. What is going to matter is that I'm consistent in how I do that. I can't make this first point, for instance, x1 and y sub 2. That's going to be a no-no. We don't want to do that. It's going to cause all sorts of problems for us. So here I have my distance formula, square root of the difference of my x coordinates squared plus the difference of my y coordinates squared. And again, it doesn't really matter which one you put first and second inside those parentheses because we're going to square it, so it's going to take care of any negatives that may arise. So when I substitute in here, I'm going to have d equals the square root of negative 4 minus 2 quantity squared plus, let's see, we're going to have 3 minus 1 quantity squared. When we simplify, here I'm going to have negative 4 minus 2, or negative 6, all squared, plus 2 all squared. Negative 6 all squared is going to give me 36. And 2 squared is going to give me 4. 36 plus 4 is going to give me 40. Now, the one thing that's kind of important in this course, if you leave this and say, all right, well, the distance between these 2 points is the square root of 40, I'm going to go ahead and mark that problem wrong, or that answer wrong, rather. Reason being is I'm able to simplify this radical, right? So just like fractions have to be simplified, if I have a radical like square root of 40 that can be simplified or broken down, I need to do so. So what I need to do is find perfect square factors in here. In this case, perfect square factor, or the largest perfect square factor, is going to be 4. 4 times 10 gives me the 40. So the square root of 40 breaks down to square root of 4 times square root of 10. And the square root of 4 is 2. So I get 2 square roots of 10 as my exact answer. So if I'm looking for an exact answer, 2 square roots of 10 is what I am looking for here. If I'm asking for a decimal approximation, then you can go ahead and punch that in your graphing calculator. But 9 times out of 10, I'm going to be looking for exact answers. So make sure that if you've forgotten how to simplify radicals, it would probably be a good idea to do a couple practice problems and look for a few back in the chapter 1 practice area, or the chapter 1 practice problems in our OpenStax book. Okay. The next formula that you guys should be familiar with is the midpoint formula. Okay, the midpoint between points A and B is found by having the sum of x coordinates, x sub 2 plus x sub 1, divided by 2. And then for the y coordinate is the sum of your y coordinates, y sub 2 plus y sub 1, all divided by 2. What am I really doing? I'm taking the average of my x coordinates, right? And then I am also taking the average of my y coordinates. And the average of my x and of my y coordinates is going to give me the actual midpoint itself. Okay? If we are working on something in 3 dimensions, we're going to have an x, a y, and also a z coordinate or component. The midpoint formula works and translates into higher dimensions. We would just add then a average of our z coordinates to find a midpoint in 3 dimensions. Okay, and this works in higher dimensions, but once we get beyond 3, we can no longer visualize it, and I don't want to do that to you guys right now. So using the midpoint formula, if I have points 1, 5, and negative 3, 8, again, if I label them x sub 1, y sub 1, and x sub 2, y sub 2, and I want to put this into my formula. So let's do the x coordinate first. I'm going to average my x coordinates. So I'm going to have 1 plus negative 3, all divided by 2. Or we're going to have negative 2 divided by 2, and I get an x coordinate for my midpoint of negative 1. For my y coordinate, I'm going to average my y coordinates, or the y coordinate of my midpoint, I'm going to average the y coordinates. So we're going to have 5 plus 8, all divided by 2, or 14 divided by 2, or I'm going to get a y coordinate for my midpoint of 7. So here my midpoint is going to be the point negative 1 and 7. Okay. Those are pretty straightforward examples for the distance and midpoint formulas. The one thing that we're probably going to run into is looking at it from a slightly different perspective. So let's say maybe we have something like we're going to use 6 again, between the point 2, negative 1, and let's do x, comma, 2. Okay, so I'm going to take my distance formula. I'm going to label x1, y1, x2, y2, and I'm going to substitute into the distance formula d equals square root of x2 minus x1 squared plus y2 minus y1 squared. Right, so when I make that substitution, we're going to have 6 squared equals square root of x minus 2 quantity squared plus, let's see, we're going to have 2 minus negative 1, or 2 plus 1 squared. So here we're going to end up with, excuse me, and I don't want 6 squared here. I'm a step ahead of myself. All right, so we're just going to have the 6. I want to square both sides so that I can cancel my square root here. That's going to give me 36 equals x minus 2 quantity squared plus 3 squared, or 9. So if I subtract 9 on both sides of my equation, here now we're going to get, let's see, we're going to get 37, or 27, pardon me, equals x minus 2 squared. So when I take a square root of both sides, now we're going to have plus or minus the square root of 27 equals x minus 2. Square root of 27 is going to simplify. we're going to have a perfect square factor of 9 times 3. So I'm going to get plus or minus 3 square roots of 3 equals x minus 2. And when I solve for x, I get x equals 2 plus or minus 3 square roots of 3. Here in this case, we're actually going to have two solutions that will satisfy this particular equation. So if I draw a quick sketch here, so I throw a little xy axis in, we have a point at 2, -1, so maybe somewhere here. And I have another point that's going to be at some x value, but have a y value of 2. So somewhere along this dotted line, I'm going to have a point, or actually 2 points, where I have a distance of 6 units from this original point that was given, right? And hopefully you guys can now see that in the illustration that I have here, that we're going to have one point that this is not necessarily drawn to scale, that's probably going to be negative, and one that's probably going to be positive, where I have a y value of 2, but we are 6 units away from that point to -1. Okay, so we're going to see some problems where you're given information, asked to use whether distance formula, midpoint formula, maybe some other formulas that you've seen in the past, but now you're going to approach it from a slightly different angle, and maybe you're going to be, in this case, like I did here, or showed you here, you're going to be given the distance and asked to find one or more of those missing coordinates, rather than just crunch the numbers and find the actual distance itself. Next thing I want to mention is talking about finding x and y intercepts. When we're finding x and y intercepts, I'm looking for where do I intercept those axes. If I'm looking for an x-intercept, I'm going to set my y value equal to 0, and I'm going to solve and find the x value that gives me that particular solution. When I'm looking for my y-intercept, I'm going to set my x value equal to 0, and I'm going to solve and find the y value that makes that true. So let's find my x-intercept here. So if I set y equal to 0, I'm going to have 4x minus 7 times 0 equals 12. 7 times 0 is simply 0, so I have 4x equals 12. Or when I divide both sides by 4, I get x equals 3. For my y-intercept, I set x equal to 0. I'm going to have 4 times 0 minus 7y equals 12. 4 times 0 is simply 0, so I have negative 7x equals 12, or I get x equals negative 12 sevenths. Okay? Two things that I want to point out here. I'm not done. Okay? My x and y intercepts are going to be points in the plane, so I need to make sure that I write these in the form of a point. So this is going to be the point 3, 0 for my x-intercept, and my y-intercept is going to be the point 0, negative 12 sevenths. Okay, it seems like a really picky thing, but if you leave those as x equals 3, or I just realized that I did that as x instead of y. This should be y equals negative 12 sevenths. Okay, but if you leave them as x equals 3 or y equals negative 12 sevenths, those are actually horizontal and vertical lines. Okay, so we have to make sure that we have them in the appropriate form. And again, because we're talking about intercepts, we're talking about points. Please write them as points. The last thing I want to point out here with this example is that I want you to use the improper fraction of negative 12 sevenths. Okay, I agree that it is equivalent to negative 1 5 sevenths, but I do not want you guys to get in the habit of using mixed numbers. Hopefully you've broken that habit in Alg 2 already, but if you haven't, I absolutely do not want you to use mixed numbers. There are a lot of cases and instances where they simply do not work for us. We need to have the improper fractions. Okay, so please use the improper fractions. Even though these are equivalent, I don't really, for our purposes here, want you using the improper fractions. Okay. 2-2. We're going to talk about some graphs. We're going to talk a little bit about point plotting, and we're going to talk a little bit about symmetry. All right, so I'm going to go through the first part here pretty quickly because I think it's relatively elementary and we should all be on the same page with it. So anytime we have any graph, whether it's a line, whether it's a quadratic, whether it's a logarithm, whether it's something that doesn't have a name, okay? Maybe it's just some crazy, awful function that we got from some model of a real world situation. I can always create a graph by plotting points. I don't necessarily always have to know how to graph it by hand. So the one thing that we can always do, if we have something, obviously I certainly hope that if we have 3x minus 2, we all know that we have a y-intercept at -2, a slope of +3, so we're going up 3 and over 1, right? And I get a series of points that look something like this, and then we can just connect the dots, and voila, we've got ourselves a nice graph of a line, okay? I sincerely hope that if we're in this class right now, we don't need to make an XY table for a graph like this, okay? But let's say we got to a graph like y equals x squared plus 4. And you say, you know what? I don't remember how to graph shift parabolas. We can always make an XY table. So what I'm going to do here real quick is I'm going to open up my graphing calculator. So I have the Calculate 84 app here on my home screen. So I'm going to open up Calculate 84. This functions just like a regular graphing calculator, or if you have your normal graphing calculator with you, you can use it. So here I can enter x squared plus 4. I can go ahead and graph it. And unfortunately, with the way I have this, I don't know how it's going to do this for the video when I switch the orientation. Hopefully we're not looking at this sideways right now. Now I have a better view when I make this vertical, but here I have a graph. All right. If I want the XY table, I'm going to press the second key and then the graph button, and it's going to give me a XY table here that I could then use to go through and plot each of these points to create the graph on a sheet of graph paper, or for whatever purpose it is that I'm creating that graph. Okay, 9 times out of 10, we're able to do that. If you remember graph shifting, it's going to save you a little bit of time, a little bit of energy, and it's going to simplify the process for you. Okay, so that's one way we could do something like that. All right, but here we ended up with a parabola that shifted up 4 units. And if we're thinking in terms of graph shifting, I get critical points here, and my parabola is going to be the U-shaped graph, and it's going to end up looking something about like this. Okay, not necessarily 100% perfect, but we're just looking for a sketch here. It's in the ballpark. It's good to go. Right. The next equation that I have here is x equals y squared minus 2. So you might be saying, well, what in the world is that? Okay, a couple of ways we could go through and do this. Right. When we're dealing with the graphing calculator, we need something that is solved for y. So if I want to solve this for y, I would essentially need to add 2 to both sides. So we get x plus 2 equals y squared. And I would have to take a square root of both sides. So I'm going to get y equals plus and minus the square root of x plus 2. So if I'm doing this in a graphing calculator, I need to enter this as 2 different equations. In y sub 1, I'm going to have the square root of x plus 2. And in y sub 2, I'm going to have the square root, or the opposite, pardon me, of the square root of x plus 2. So if I go back to my graphing calculator app here, I would have the square root of x plus 2. And in my second equation, I'm going to have the opposite of the square root of x plus 2. And when I graph it, you'll notice, and again, I'm going to try the vertical thing here. You'll notice that I get what looks like a parabola on its side. Okay, when I have x equals y squared, I have what we refer to as a sleeping parabola. It's a parabola that's laid over on its side. Right? If you think about it, if I split this into 2 equations using, say, piecewise function or a set of brackets, I have square root of x plus 2 and the opposite of the square root of x plus 2. If I graph each of these individually, the first one, it's a square root function that shifted 2 units to the left and is going to look something like this. The second one is the opposite of the square root of x plus 2, so it's going to have flipped upside down and then shifted 2 units to the left, and I'm going to have something that looks like this, and we end up with this sleeping parabola on its side that we saw from the graphing calculator. And again, I could generate then the XY table for this and come up with those values. and fill in my chart here. But what I really wanted to show you guys is how we can go into the graphing calculator, how we can generate the XY table, and how we can come up with some of these values. Okay. One thing I do want to point out is notice that if I come in here, I do get some errors. So like -3 gives me an error. Why is that? Well, think about it. I have the square root of x plus 2. If I put an x value of -3 in there, I'm going to have the square root of -3 plus 2, which is square root of -1. That's going to be an imaginary answer or imaginary number, and my Cartesian plane is simply the real numbers by real numbers. This is not my imaginary axes. All right, that's a whole different unit. That's a whole different topic. And right now we're not dealing with complex numbers. So those values, once we got below, in this case, -2, we're going to have a complex solution, and therefore we're going to have no real answer for that particular value. All right, and our graph just doesn't exist there. All right. Let's talk a little bit about symmetry. So when we're talking about equations and graphs, and I'm ignoring some of the function rules, if you remember the function rules from Alg 2, all right? We have symmetry about the x-axis, where I have essentially the same reflected picture or graph above and below my horizontal axis, all right? So for each point x, y on the graph, I then have to also have the same x value with the opposite y. So x negative y has to also be on that graph. All right, they're reflections about the x-axis. We have symmetry about the y-axis. So similarly, if I have the point xy on the plane, I also need to have negative x, y as a point on the plane for every point x and y. All right, perfect example for symmetry about the y-axis is parabolas or absolute value, okay, or at least some of those functions depending on how they shift or where they're at in the plane. And we also have symmetry about the origin. All right, symmetry about the origin for every point x, y on the graph, the point -x, -y must also be on the graph. You can think of symmetry about the origin as either a rotation of 180 degrees, all right, or you can think about it as a reflection over x and then a reflection over y, or vice versa, reflection over y, then a reflection over x, and you will still get that same origin symmetry. Okay, we do have some tests for each of these, and the tests are the following. So symmetry with respect to the y-axis. I'm going to substitute a -x in for x everywhere in my original equation, and I'm going to try and simplify it. If I get my original equation back, I have symmetry with respect to the y-axis. So my example would be something like y equals 4x squared. If I replace x with its opposite, I have y equals 4 times the opposite of x squared. And if I simplify by squaring -x, I get y equals 4x squared. This checks, so I have symmetry with respect to the y-axis. Okay. Symmetry with respect to the x-axis. I'm going to do almost the same process, except I'm going to substitute the opposite of y for y, and I'm going to see if I lead to the exact same equation. So again, a relatively straightforward example. If I had y squared equals 3x plus 1. Okay. If I substitute y or opposite of y for y squared, I would have the opposite of y all squared equals 3x plus 1. If I square the opposite of y, I get simply y squared equals 3x plus 1, and I did in fact get the exact same equation. So here I would have symmetry with respect to the x-axis. Okay, and last but not least, for our test for symmetry with respect to the origin, we're going to substitute both -x for x and -y for y. So if I have an equation like x squared plus y to the 4th equals 5. Okay, if I substitute that in, I'm going to have the opposite of x squared plus the opposite of y to the 4th power equals 5. Anything raised to an even power guarantees that positivity. So here I'm going to end up with x squared plus y to the 4th equals 5. and this would check out, and I would have symmetry with respect to the origin. Okay. It is possible for you to have more than one type of symmetry when we're dealing with equations. Once we start dealing with functions, that's typically not going to be the case, because if you have multiple types of symmetry, you've probably broken some rules for functions. But if you look at this last example that I put down here, x squared plus y to the fourth equals 5, not only did it pass the origin symmetry test, it would also pass the x-axis and also the y-axis symmetry tests as well. Okay, so we can get multiple types of symmetry for a particular equation. All right, that just because you found one doesn't mean you're necessarily done. You should probably at least look at and or test for all three. Okay, so testing for symmetry, we want to determine if it exists. Here I've got y equals x squared minus 4. If I test for, let's say, x-axis, all right, I'm going to substitute y with the opposite of y. So here I'm going to have the opposite of y equals x squared minus 4. There's nothing really that I can simplify. So no, I don't have x-axis symmetry. If I test for y-axis symmetry, I'm going to replace x with the opposite. So we're going to have y equals the opposite of x all squared minus 4. Here we're going to end up with y equals x squared minus 4. This does check out. Okay. If I go to test, I'll let me my check mark into a triangle there. Right. If I go to check origin symmetry, right, and I replace both, I'm going to have the opposite of y equals the opposite of x squared minus 4. The left-hand side of my equation, I'm still going to have the opposite of y, if I can actually write neatly tonight, sorry, equals x squared minus 4. All right, so even though part of my equation went back to the original, I don't have the complete original equation. All right, so the only type of symmetry I have here is going to be y-axis. So here I have symmetry with respect to the y-axis. Okay. If I take a look at the next one, same deal. If I go through, let's test x-axis symmetry. Right, I'm going to replace y with its opposite. Nothing simplifies, doesn't work. If I test y-axis symmetry, I'm going to replace x with its opposite. And when I simplify the opposite of x cubed, I'm going to get negative x cubed plus 2. This one doesn't work. If I try to check origin symmetry, right, I'm going to have the opposite of y equals the opposite of x cubed, opposite of x, pardon me, all cubed, plus 2. When I simplify, I get negative y equals the opposite of x cubed plus 2. I could multiply both sides here by negative 1. When I do that, I get y equals x cubed minus 2. Almost everything came back to its original except for now this constant. Therefore, it fails the origin symmetry test as well. So here we have no symmetry. Okay. Last but not least, I'm going to take a look at a circle here, right? So if I go to check x-axis symmetry, I'm going to replace y with its opposite. And when I simplify, I get x squared plus y squared equals 25. This checks for x-axis symmetry. When I check for y-axis symmetry, I'm going to replace x with its opposite. And I'm going to try and simplify. When I do so, I get x squared plus y squared equals 25. And this checks as well. When I check for origin symmetry, I replace both x and y with their opposites. And when I simplify, I get x squared plus y squared equals 25, and this checks. So in this case, the circle that I have here, this is a circle centered at the point 0, 0 with a radius of 5 units. This has symmetry with respect to the x-axis, y-axis, and origin. Okay, we're going to do some more with circles coming up, so if you've kind of forgot how I came up with the center and the radius of this circle, don't worry about it. It's coming here in a couple of days. This is all I have for you guys for the first 2 sections. Hopefully that first set of notes wasn't too bad. And I'll see you guys tomorrow in class. Have a good night.